Hi everyone, welcome to Optimize AI Lecture 2, the top 3 parallelism that you will need as an AI engineer. You might have heard of many parallelism. Why only 3? Because we are focusing on the inference field, which has those 3 components as the most important. After this lecture, you will know how to execute those parallelism in engines like VLLM, SGLane, and TensorRT LLM. In addition, we have some bonus, which is some interview questions from the industry. If you want a complete AI engineering roadmap, feel free to check out the Substack of Faradon's AI report. Covered the first optimization technique, linked to the YouTube video below. Now we are on the second lecture on parallelism. So why study parallelism? As the model sizes are growing, we need more compute and more memory. Previously, it was 1.5 billion, but now we have 75 billion and even 530 billion. So what problems are we seeing with the increasing model sizes? First, it is compute. Each GPU can only process that much. Although you heard of supercomputers, is it making one chip super fast or putting together multiple medium-level chips but let them do the work in parallel? It turns out, for supercomputers, we are just using the normal laptops but plugging multiple of them together. And that's why we need parallelism. And secondly, on the memory side, can one model fit on one GPU anymore? With the small models, you can easily fit on an A100, but for the bigger models, you might need 8 times A100. How to execute those parallelism on your own? It's very simple. You just open one terminal and open the command of, say, SGLane, and then pass in --tp equals to 2 or tp equals to 4 to turn on the tensor parallelism. So what will the improvement be? It's 28% improvement versus no parallelism baseline. And you can try this on your own. All the commands are attached below. What to take away from this lecture? There are 3 interview questions that you will master. One is throughput versus latency. Which technique is good for throughput and which one improves latency? In addition, for each of the technique, is it better for smaller batch size or better for large batch size? Third, what are the trade-offs of using parallelism, such as communication and bandwidth? The first technique is tensor parallelism. The idea is very simple. The problem it solves is one model cannot fit on a GPU. So we just split this model into, say, 3 or 4 shards. This will let GPU load one shard. But how does it work mathematically? Don't worry. So to calculate QKV, we need the input X and multiply by the weight matrix of WQ to get Q. So what does WQ look like? This is WQ. Here is the input X. But why are there 3 colors? Because it's multi-head attention, MHA. Therefore, how many heads are here? The number of heads is 3. So each of them is this WQ. And we multiply X and get this head output of Q. And then for the second head, this green box, we use the same X to multiply with the green head 2 and then get this output Q2. How can we divide it into different GPUs? So with one GPU, we compute those 3 multi-head attention together and return this big chunk of result. But if you have 3 GPUs, how to divide it? Yeah, instead of one big chunk, we just divide each of them into one GPU. And finally, we concatenate those 3 heads together. In a more visual example, say given the input X, instead of using 1, we split it into 3 shards. So after each of them computes its own result, what else do we need? What communication strategy do we need? Is it all gather or all reduce? Turns out it is all reduce since we need to combine those 3 heads together. And what does all reduce mean? Is it 1 pass to 2, 2 pass to 3? No. It is head 1 passing to all of the other workers, head 2 to all the other workers, and head 3 to all the others. And that's why this all reduce is n-squared communication, and that's why tensor parallelism needs this O-reduced communication. Now, interview time. DeepSeek V3 is the latest large model, and B200 is the most powerful GPU. How many B200 GPU do we need to deploy this big model? Consider B200 GPU by NVIDIA has 192 gigs of memory, and the model has 671 billions of parameters. If we use FP8, how much memory will it take? Since FP8 is 1 byte per parameter, we multiply by 1, so it's 671 gigabytes. Now, how many B200 do we need? We divide 671 by 192, which is around 4 GPU. That's why we will need 4 B200 to shard this model, and this TP size will be. Here is the second interview question. Is tensor parallelism good for small batch size or large batch size? I will let you think, and while we move on to the next section. What are some concerns about tensor parallelism? Is it always good? So for the latest architecture, it introduces multi-head latent attention. So it's not only heads, but now just 1 KV head. If we have 3 GPUs, what to do? We will have to duplicate the KV heads, right? Since although Q, we have 3 Q, but for KV, we have a single head. Is that a lot of waste? Yes. That's why tensor parallelism doesn't lead to a lot of duplication for multi-head latent attention, but also for group query attention, which is less KV head than the number of GPUs. How to solve this problem? Enters data parallelism. It will solve the duplicated KV results for the previous. How to solve it? It divides the big input batch into smaller pieces. So batch 1 has the first 2 requests, and batch 2 has the second 2 requests. If the inputs are different, will the KV value be the same or different? Although we are duplicating the model 2 times, so that the WK and WV are the same, but the input is changed, the output will also be different. And this KV, you might ask what KV means. It's just the computation result of X multiplied by WK. Now, a quick quiz. For data parallelism, what is being split? Since the model is no longer split, right? It is the data that is being split. What is being replicated? The model. We duplicate the weights WK, WV, WQ onto each of the GPUs. Now to recap, what about tensor parallelism? What is being split? Is it data or model? It is model, since we cut the big matrix into 3 parts. What is being replicated? The same data will pass through all of these shards. So we have the same data going through all of the GPUs. Another important question: what is data parallelism good for? Is it good for large batch size or small batch size? What does batch size mean? It means one batch of data, say with 4 requests. So if it's a large batch, we can easily divide each request to 1 GPU. So the bigger the batch size, the happier the GPU. But for tensor parallelism, is it good for big batch size or small batch size? It turns out to be the small batch size. Do you know why? Consider the communication. Say that for TP, we have 3 GPUs. Each of them will broadcast its results to all the other workers. What will the communication cost be if the batch size gets large? If it's larger batch size, this output will be larger, so it needs to spread more data, right? It will send more data through the Ethernet, or IB, Infinite Band, or NVLink. Therefore, the communication will be bigger. So by reducing the batch size, we can save on communication. Now for DP, data parallelism, what are some concerns? We are duplicating the model many times. The same weights duplicated. So what does it cost? It costs a lot of memory. But is it that bad for memory? Turns out it's not that stress on memory, because although the weights are duplicated, but the KV are sharded. They are unique for each GPU. Why? Because the input are different. Although the weights are the same, they will result in different outputs. So that's called KV sharding. So this computation results are sharded, but the weights are duplicated. But both of them are memory related. That's why DP attention it even saves memory. Alright, after we optimize the attention with two parallelisms, what else can we optimize? What else are in this transformer layer? There is FFN, the feed-forward neural network, right? How can we optimize that? We use expert parallelism. What problem is it solving? The feed-forward neural network is very dense. By dense, we mean it's just a gigantic matrix, which consumes a lot of compute. Since the bigger the matrix, you need to calculate many numbers. If we have multiple GPU, how can we make it faster? Let's divide it into different shards so that each GPU can compute a small sparse matrix. But wouldn't that the same as tensor parallelism as attention? Well, there is a slight difference. It is because not all the experts are activated. For tensor parallelism, we need all the shards to be computed. But for expert parallelism, we choose some of the expert to compute a result using a router, whereas we just leave the other experts untouched. That's what name sparse comes from. It will leave some expert empty. Why do we need MoE? So why this sparsity helps? On the graph here, the x-axis is the number of activated parameters, which is compute. The more parameters activated means how much floating point operations, like those activated numbers, are needed. On the y-axis, it is the performance, say MMLU, this benchmark. We can think of it as the intelligence of the model. With the same compute, this Mistral 7B has this around 50 levels of intelligence, whereas DeepSeek with MoE suddenly has this 80 level of intelligence. So the same number of compute, but a much higher intelligence or performance. Why? Think about in the perspective of sparsity. It's because DeepSeek is a bigger model. That's why it can achieve a better intelligence, but it doesn't need consume more compute. So bigger brain, but same compute. How does it do it? For each token, we select these four experts, and that's why we don't need that much compute. In this example, the original model is the dense model is like this, and now we use top four. So route to these top four routers. However, we have some more experts so that our brain is bigger than the dense model. So we can store knowledge of the world inside our brain. Although in the compute time, we are as efficient as the smaller brain. So in the industry, how many experts do we need? On the graph above, we have 6 experts, but for DeepSeek V3, we have 256 experts, and 8 of them are activated. So do we want the more expert or less experts? As you see, at first, DeepSeek V1, they have only 64, but suddenly, a year later, they have 4 times the amount of the number of experts. So do we want more expert or less expert? That means, do we want big expert but less of them, or more small expert? Turns out that this fine-grained expert is better. On the orange line, this is 63 experts, and the blue is only 10 experts. As you see on different benchmarks, the more experts, the better. Are there any concerns for a mixture of expert model? We heard all those good stuff, but what are some concerns? It performs really well in theory, but on the system, we need to solve an engineering challenge, which is, what if some experts are activated all the time and some are not activated? How to balance the load. This will need a smart router so that we don't let one GPU burn out. Now for the final section. It is the bonus. What are some interview questions? might look like, and what are some real industry deployment concerns of engineering. If you see this configuration on, say, VLLM or TRT LLM, what does that mean? How many GPU do you actually need to support this config? Data parallelism equals to 2, tensor parallelism equals to 4. How many GPUs do you need to reserve? How to think of this problem? First, for data parallelism, each data parallel will mean an entire model. So if we have dp equals to 2, how many models do we need? We will need 2 entire models. And now within the model, how many shards are we having? Tensor parallelism of 4 means 4 shards. So that means 4 GPU per model. On the graph on the right, we have this model 1 and then a duplicated model 2. Each of them has 4 shards. So we need 4 GPUs for each. Together, how many? It's total of 8, which is 2 times 4, which is dp times dp equals to 8 number of GPUs. So remember this formula of dp times TP will give you the number of total GPUs. This second question is, for tensor parallelism, should we deploy it intranode or internode for tensor parallelism? Intranode means within one server. So this server has 8 GPUs. This is an intranode within a server, whereas internode is across servers. For tensor parallelism, which choice should you make? Is it within the server or spread across different servers? Let's give a hint. For intranode, the bandwidth is high. So the connection is usually NVLink by NVIDIA, which is a super high speed communication protocol, whereas internode is usually Ethernet or InfiniBand, which is slower. So tensor parallelism, does it require a lot of communication? Yes, since it's an all-to-all communication, right? Each of the GPUs, after computing its shards, needs to send to all of these neighbors. Therefore, we need a big bandwidth, so the intranode communication deployment strategy is needed. So what can be used for internode? Pipeline parallelism. Why? Because it is an end-to-end, point-to-point communication. So on the graph on the left, worker 1 will pass its results to worker 2 to 3, and 3 to 4. It is this pipeline fashion which doesn't need that much of communication as the first tensor parallelism PP. For data parallelism, you might heard of 0DP or FSDP. Can it be used on inference, or are they more designed for training? Turns out those are for training. So why not for inference? Because for training, they will need to shard the gradient, the parameters, and also optimize their states. But for inference, the data parallelism, we only need to shard the KV. So fully sharded data parallelism, after each instance computes their result, they need the full gradient over all of these within batch data. So they need an O-reduce to communicate all of the gradients, whereas for inference, we don't need the O-reduce. Therefore, we don't need fully sharded data parallelism to shard those gradients. We just need to shard the KV cache. That's why we use DP. Attention DP for inference, whereas FSDP for training. Now, for expert parallelism, what are some challenges? If the router is poorly designed, we have those input tokens, a series of verbs. And expert 1 is for processing verbs, and expert 2 is good at processing nouns. What will happen if the input is all verbs? The router will route the 4 requests all to expert 1. And what will happen to this expert on this GPU? It will be overloaded, right? And the other GPUs are idle. So how can we make all of them have an equally amount of a wear out, not let one of them burn out? The idea is to assign a capacity for each. Say my capacity is 2, so all of them can handle only 2 requests per batch. But what if the request is all verbs, have 4 verbs? We will need some redundant experts. What does the redundant do? It will copy the weight weights of Expert 1 onto those 2 empty GPUs. So now we have 3 GPUs acting as Expert 1. So we increased Expert 1's capacity to 3 GPUs. This is called redundant experts. Finally, why doesn't DeepSeek use tensor parallelism during the training? But in inference, it uses tensor parallelism all the time. It's because O2O communication. So how is that different from training versus inference? In training, we have a forward and a backward pass, right? So the backward pass, we have 2 times the compute, and this O2O will be too burdensome, too much communication. Whereas inference, we just have the forward pass. Therefore, the communication is not as intensive. Then in the next lecture, we will talk about the rest of the optimization techniques. Thank you for watching.